This session introduces the exponential weighted moving average model for seasonal data. The concept is intuitive, but keeping track of all of the subscripts and the computations can be confusing. For that reason, I'm first going to develop a couple of naive models based on the random walk concept so you can see the subscripts with a minimum of computations. Then we will introduce the exponential weighted moving average computations. Here are some data showing the quarterly sales of a retail product. The title scanned sales means that this is the number of units sold at checkout. As you can see, this product sells about 1.5 times as much in the fourth quarter as it does in the other quarters. So this could be something that sells a lot during the holiday season. So we have a seasonal time series, and the number of periods in a season is equal to 4 because there are 4 quarters per year. And we call that number 4 S. Notice also that the sales are trending downward, so we will eventually need to capture both the seasonal pattern and the trend in our model. What is the most simple way that you could forecast such a time series? Well, suppose it's the fourth quarter in 2005, and you want to forecast the first quarter of 2006. One rule would be to say, just go back to the first quarter of 2005 and use that as a forecast. So the forecast that I would make in period T for period T plus 1 is simply Z sub T minus 3. Now let's introduce another forecasting rule. In this case, let's suppose I'm starting in first quarter of 2006 and I'm forecasting the second quarter of 2006. And like before, I would start with using the second quarter of the previous year as my forecast. For example, that would be second quarter of 2005, and that quarter and the forecast are highlighted in yellow. But then you might say, the current quarter that I'm in right now is lower than it was last year. And so therefore I should expect the next quarter to be lower than it was last year. And I would say, how much lower? And you would say, first quarter of 2006 is lower than first quarter 2005 by minus 1,132,896 units. Should I use that to adjust my forecast? I would say, yeah, that sounds like a good idea. So if we are in first quarter 2006 and I'm forecasting second quarter, I start by using second quarter 2005, and then I add to that the difference between what I observed in the current quarter and what I observed in this same quarter a year ago. So in this case, we're going to adjust our forecast down. So the forecast is what I observed in the quarter that I'm forecasting a year ago, but plus the difference between the current quarter and this same quarter a year ago. Now let's extend that concept. Rather than just use the same quarter from last year, let's use an exponentially weighted moving average of the same quarter in all previous years. And I'm going to call that exponentially weighted moving average my seasonal profile. For example, let's focus in on the first quarters. I will initialize the very first quarter of 2005 just by setting that value to the observed value. That's the first row showing 32,655 and 182. Then in the fifth row, when first quarter rolls around in the second year, 2006, I update that first quarter profile using exponential smoothing. And I'll do that again a year from now and so forth. And of course, I'm also doing the same thing for all of the second quarters, third quarters, and fourth quarters. Now the weight that I place on the most recent quarter is denoted using a capital lambda. It looks like an upside down V. Now, rather than looking at how much the current quarter differs from the same quarter of the previous year, let's look at how much it deviated from the most recently computed seasonal profile for the same quarter. So it's the seasonal profile of the same quarter in the previous year. For example, in first quarter 2006, I observed sales of $31,522,286, and from that I subtract the seasonal profile of first quarter 2005, and I'm going to call this the deviation from the seasonal profile, and the two numbers used are showed highlighted in yellow there. And then that shows you where you put the results of the computation. Now this might be a little bit confusing because in the first year that I'm doing this, I will get the same deviation as I did before with random walks because of the way that I'm initializing the seasonal profile for the first year. But in later years, they will be different because then the seasonal profile becomes an exponentially smooth value rather than raw values. And then a rather obvious thing to ask is, why not also apply exponential smoothing to track the deviations? And that is exactly what we do. The weight that we place on the most recent deviation is called little lambda or lowercase lambda. So I initialize my exponentially weighted moving average of the deviations by first setting it to the first deviation that I have computed, the one for the first quarter of the second year. Then I start updating using exponential smoothing. And here I have combined the deviation of second quarter 2006 with the smooth deviation of the previous quarter to get a new smooth deviation for second quarter of 2006. The new smooth deviation for the fifth quarter, or second quarter 2006, is minus 962,796. That number is saying this: as of the second quarter of 2006, this is an estimate of how much the actuals will differ from the seasonal profile of the same quarter of the previous year. How do you get a forecast? Well, if you've already figured it out, that's really good because that's the reason I took you through the logic of the random walk models. The logic is the same here, except that you combine smooth values rather than raw values to compute the forecast. So I'm in the first quarter of 2006 and I want to forecast second quarter 2006. I start with the seasonal profile of second quarter 2005. Then I adjust it by adding the exponentially weighted moving average of the deviations in the current quarter, which is first quarter 2006. So what I'm saying is the starting estimate of the forecast of second quarter sales in 2006 is the profile of the first quarter computed 3 quarters ago, which was 31655,182. But according to the exponentially weighted moving average of my deviations, we're currently running about 1,132,896 units below that. So I want to adjust my starting forecast by that amount. So I add those two numbers to get a forecast. Again, the numbers here look like the random walk numbers because my exponential smoothing is not kicked in yet. To find the best values of capital lambda and lambda, I just use solver to minimize the mean squared error or the standard error, either one. One's just the square root of the other. Here are the results, and there's some issues there that I'll show you later, but we've just plotted the actual versus the forecast. I didn't put upper and lower bounds on it because it just made the graph too messy. Here's a control chart of the errors, and I see some problems, but we're going to talk about that in a later class. Specifically, the problem I see, there's a run of 8 positive errors, which meant for 2 whole years the model was under forecasting. Here is the autocorrelation function of the errors. I see a problem there, but we'll talk about it later. For example, there's a strong positive autocorrelation at lag 1, and that is not okay. So don't worry about understanding how to fix the problem yet. I'm just pointing it out that the model didn't fit the data the way we would like, and we'll learn how to fix it later. So stay tuned.